All right. Well, good morning again, everyone. I'm Professor Bob White. It's indeed my pleasure to welcome you to the 67th Engineering Design Conference for Senior Projects, hosted by the College of Engineering and Applied Sciences. This session is hosted by the Department of Industrial and Entrepreneurial Engineering and Engineering Management. We're very pleased you're able to be with us this morning. This is our second virtual conference, and we're happy the technology allows all of us to come together in this way. There are several groups who want to extend a very warm welcome to, and that includes fellow students, faculty, visitors, friends, alumni, and project sponsors. Thank you for being here supporting this group of students. Particular recognition is given to our faculty. Dana Hammond. Dana is the coordinator of our senior projects, and she does a fabulous job. Thank you very much, Dana. We all appreciate your work. Other faculty that are with us this morning, and I apologize if I've missed anybody, but I hope I have everyone. Professor Jim Burns, Professor Tom Schwartz, Professor Tim Green, Professor Tycho Fredericks, Professor Tarun Gupta, and Professor Azim Hoshiar. They are all very instrumental in helping these students as we go through the senior design process. Another group that we extend a particularly warm welcome to is family members. While it's not always possible for family members to be with us, when they can be, we like to explicitly recognize them and all the contributions they've made to help these students be in the position that they are. For Nick Randall, we have his mom, Deborah Randall. Deborah, if you're there and you want to turn on your screen, we're very happy that you're with us this morning. And for Jonathan, we have Makeba Massey. Makeba, if you're here with us and want to turn on your screen so we can recognize you, we again are very happy that both of you are with us this morning. These students, these almost engineers, are very thankful for all the love and support that everyone has given them to put them in the position to be able to present their senior projects today. It's a very exciting and proud day for our seniors. They came to us several years ago as freshmen, and it has indeed been our pleasure as faculty members to have worked with these students and help them achieve their goal of becoming an industrial engineer. They've worked very hard on the projects, and I think you're going to be very impressed with what you see in our second presentation this morning. This presentation is Distribution Center Layout Optimization. Team members, Cameron Church, Nick Randall, Jake Sikowski, and Jonathan Worthy, and industrial sponsor, Mike Eldridge. Take it away, folks.
Okay. Good morning, everyone, and thank you for attending our presentation. We greatly appreciate it. My name is Jake Sikowski, and our project is the Distribution Center Product Location Optimization Project.
I did fine until I...
So this is our team. Nick Randall is pictured on the left, then John Worthy, then myself, then Cameron Church. Next is our sponsors. Our academic sponsors are Dr. Jim Burns and Dr. Lee Wells. Both are assistant professors here at Western and are part of the Industrial Engineering Department. Our corporate sponsor, who we are extremely grateful for letting us in his business, is Mike Eldridge, who owns and operates Safety Glasses USA. On today's agenda, we're going to be going over some of the company's background, our root cause and analysis, which is part of our discussion with our sponsor, Mike, our current situation analysis, our proposed layouts and how we came up with them, analyzing our proposed layouts and how they are an improvement. Then we will discuss our recommendations and then conclude the project. Lastly, we will give you guys some time at the end to ask any questions about anything you hear in this presentation today. So for the introduction and background, we're going to go over what the company is like with some of the terminology that we will be using. Here for the company background, they're located in Three Rivers, Michigan. They have around 12 employees, so they're a relatively small facility. They've been at this location since 2006, and the majority of their sales is e-commerce, but they do have a showroom on site where you can go and purchase items in person during normal business hours. Despite the name, Safety Glasses USA sells more than just safety glasses. They also sell face shields, gloves, and other PPE related products. So to get an idea of how much inventory that this company pushes around, they have around 3,563 SKUs, and they process about 160 orders a day. Due to COVID, they've seen a sales increase of 192%. around the time that the virus started to spread in the late spring. As you can see on the chart in the upper right-hand corner, the sales per month for 2019 are represented by the darker color, and the green bars are sales per month in 2020. You can see that the sales from the last year are much more consistent than the sales of 2020 due to COVID-19. This is why Safety Glasses USA could benefit from a system that dynamically adapts to the inventory model. To the changes in demand, like the one seen in 2020, the chart below shows the same data but by quarter, just as an additional visual representation. So for terminology, these are a lot of the terms you're going to be seeing throughout the presentation today. The first one is SKU, which is a code name associated with each individual product in their inventory system. Then you'll see pick, and this is the act of getting the item from its location. The pick list, which is a list of items that the employee refers to when going to pick the items from its location. And then the pick time, which is the total time, which is the time that a worker takes to grab the pick list, pick an order, and then take it to shipping. Total time is the time taken to complete all the orders in a specified period, whether it be day, quarter, or month, and so on.
Okay, so we'll give you a general overview of what the facility looks like. Here's just a general picture from a top-down view. Starting from the far left is where the printer is. This is where the worker picks up the pick list. In the middle area, we have the general inventory storage. On the far right, we have the shipping area. And at the very top, in the middle, we have the storage and overflow area. And so here's that storage and overflow area that I just spoke about. Due to their increase in demand, they're actually currently running out of standard storage space. And so they're having to utilize the middle aisle to keep their products and ensure that they're still organized and able to pick the items that they need. And so here's an overview of the general storage area where they keep their inventory. And so in the picture on the left, you can see the multiple rows. And then on the right-hand side, you can see a closer view of what the row consists of. And here's the shipping area. They actually have 3 lanes. Each is unique. The first one of the lanes is for Amazon, eBay, and other orders that have to be out in the same day. A second lane is used for standard ground shipping, and then lastly, one's used for UPS shipping. And so here's a breakdown of the shelves. The far left is a picture of a standard shelf. As you can see from the grid, it can store up to 20 items, and then this makes up one location within the overview. And in the middle, you can see the aisle overflow. This is where they keep some of the extra inventory specifically for each row stored at. And then on the right is kind of a unique shelf that they use for some of their smaller product, such as earplugs and individual lenses. And so now we'll walk you through an example of an order that a worker goes through and picks. So you first start at the printer on the far left-hand side. From there, you pick up a pick list. In the top right-hand side of this slide, you can see an example of the pick list. For this pick list, there's 3 items. However, this is not how every item or every order looks like. You can range from 1 item all the way up to 37 items. On the far left-hand side, you can see the item that the worker is picking. And then on the right-hand side of the pick list, you can see the location that it's located at. So once they have this pick list, they then go into their storage area. We naturally, as people, take the shortest path from location to location. And so our model that we developed later mimics that. And so they take the shortest path to the first shelf, and then they go to the next shelf, grab the item, proceed to the third shelf, grab the item, and then drop off the item finally at the shipping area to be packed and shipped to the customer. And so now we'll go into our root cause analysis.
Thanks, Nick. So our first step in our root cause analysis was to actually go to Safety Glasses USA and talk to Mike. And so when we did that, Mike told us that the facility needs to meet an increased demand. And his suggestion was to do that by reducing the pick time of the items. And why is that important, or why did we try to do that? It's because we can increase the overall throughput and reduce our time, and then also make cost savings with this. And so now I'd like to go through what's called the 5 whys analysis of Safety Glasses USA. And so the problem was we were meeting, or Safety Glasses USA was having trouble meeting their increased demand. And why is that? It's because their throughput stayed constant. And why? It's because they couldn't fulfill their orders. Why? So as Nick mentioned, Amazon and eBay orders are prioritized, and shorter orders are also prioritized. So why? So because of long handling times. And why is that? It's because the items are not in their optimized locations. And so that leads us to our objective statement: to reduce item pick times through item location optimization.
So now we'll go into an analysis of the current situation. And this is important to perform because when we start making changes to item locations and facility layout, it's important to have a baseline to compare back to so that we can see if our changes are actually relating to improvements for the company. So the first step of this was data pre-processing, which consists of cleaning and restructuring the data that we received so that we can then go into our 6 analysis techniques. The first being creating heat maps, which are used to visually plot where the highest volume of orders are coming from within the system. Next was Pareto analysis to analyze which SKUs were the most important. Next was control charts to analyze upwards and downwards trends within SKUs, which will help us relocate SKUs when needed. Next is market basket analysis so that we can identify which SKUs are commonly sold together. Next is layout generation, which is where we create new layouts. And then lastly is Monte Carlo simulation, which we use to analyze our new layouts. So the first technique was creating heat maps, and these heat maps are based on the number of visits to each location within the facility. So every time a worker visits a location, the picks for that location increases, and that location becomes darker on this map. And also these maps are normalized. So the total number of picks for a location are divided by the total number of picks for the system so that these heat maps can be compared throughout time. So we start here in January, and you can see that a lot of the heat within the system is located in aisles B, C, and D, and this trend continues throughout February and March, as well as April. And then going into May, you can see that overstock of the area becoming very dark, and this is because a lot of personal protective equipment related to the COVID pandemic is located in the overstock area, and these SKUs formerly did not have a home, so they were thrown into this overstock area, and this trend continues throughout June and July. Going into August, you can see that overstock area becoming less popular and some more of the heat being relocated towards the center of the facility. And then this trend continues into September.
So now we'll get into the control charts. As John had mentioned, the heat map does a great job of showing our team where, what location within the facility items are being frequently picked from. However, for us to optimize the location and where items are located, we have to look at an individual item perspective. And so we use a control chart to look at how an individual item is being picked throughout time. And so our team used the Bernoulli QSUM chart as it continuously tracks the system. The chart itself is dependent upon 3 inputs: the probability of the item being in control, the probability of it being out of control, and if an item appears within that specific order. And so this control chart was ran over the actual sales of the first 3 quarters of Safety Glasses USA. On the right hand side, this control chart specifically is for the SKU Med 1004, otherwise known as a medical mask. As you can see, throughout much of the first quarter, the mask wasn't purchased at all. And so we established a control limit at what we felt was a normal level of purchase. And then as you can see in the second quarter and towards the end of the start of the third quarter, that during the mask mandate, it was purchased frequently, causing it to fall out of control. And so another technique that we looked at was the market basket analysis. The market basket analysis uses the frequent pattern growth algorithm. A tremendous example of this that is easily relatable is when you purchase an item on Amazon, the frequently bought together section at the bottom is actually pairing together items that other customers bought with the item that you're currently looking at. And so we went about this in order to see if we could link items together when we move them. However, when we performed this analysis, due to the small percentage of orders containing multiple items, there was no correlation found linking items together. So we were back to moving items individually. And so that led us into our Pareto analysis. Having over 3,500 SKUs, it's not feasible for our team to examine all the SKUs at once. And so we used the Pareto analysis and chose to look at the top 20% of their sales, which is about 60 items.
So in order to Move further with finding order pick times and potential time savings. We created a matrix to provide the distance information between each item location. Next, we needed a program that behaved like an experienced employee, as Nick mentioned, that would pick a series of items in the most efficient way, like a worker would. This means that the program looks at all the locations and picks them in a sequence that minimizes the total distance traveled by the employee picking the items. Next, we needed outputs from this program that gave us pick times for each layout, the original layout, our first iteration, and our second iteration, so that we could compare them. Next, Cam is going to discuss more on how this program was constructed.
Thank you, Jake. So this is an overview of basically how the Monte Carlo simulation works. So the simulation takes relevant data from Excel, such as the actual orders data, the time to grab the items at the shelf, the standard deviation of grabbing the time of the grab time at the shelf, and feeds it into a model on a quarterly basis. This data is uniformly distributed. The model then runs Dijkstra's algorithm, and that finds the shortest path, because as we talked about, humans naturally find the easiest way or the quickest way to do something. And so that's how an actual worker would travel in the facility. The simulation then generates a random pick list and goes through all the possible permutations of these random pick lists. It then selects the best one for the shortest path. It adds the printer to the beginning and the shipping area to the end. And then it carries out that path, converts the distance to time, and outputs our pick times, which is the metric we're concerned about. So simulation. So this is a little snippet of how a worker would move in the facility. And why this was relevant is it's because it provided our data for our layout verification, our proposed layout verification.
So now we'll get into our proposed layouts where we had hope, or where we generate layouts to reduce total pick times within the facility. So getting into proposed layout 1, this layout is based on moving the top products of each quarter. And 60 SKUs were moved during each quarter, which always is enough to cover the top 20% of SKUs, which Nick touched on with the Pareto analysis. So in this layout, SKUs were moved to vacant locations along aisle E. And this aisle is important because it's directly in between the printer where orders are generated and the beginning of the shipping area. So workers are able to just grab orders along aisle E and then drop them off right at the beginning of the shipping area. Looking at the picture on the right, you can see that a lot of the heat within the system is now condensed in these locations along aisle E. And like I said, pickers can just go and drop off the orders right at the shipping area from there. Going into the second proposed layout, again, this layout is based on moving the top 60 products of each quarter. And we noticed that there was some available area above the shipping area where we could actually build a new kind of hot seasonal area. And there was enough space to relocate 3 shelves there, each containing 20 SKUs for a total of 60 SKU locations. Looking at the picture on the right, you can see where that hot seasonal area was generated, and a lot of the bulk of the heat within the system is now condensed there. And then from there, pickers can go and drop off the orders right at the beginning of the shipping area. So now we'll go into an analysis of these 2 proposed layouts. This slide shows the histograms of each layout for quarter 1. These histograms show the frequency of pick times in minutes for each layout. So just quarter 1 is shown because the results are similar for quarter 2 and for quarter 3. So for redundancy's sake, we're just showing these. Looking at the top left histogram, this is the histogram for the base case. And you see that the average time is around 6 minutes. And the top right is the histogram for layout 1, and with the average time being around 5 minutes. And in the bottom left is the histogram for layout 2, with the average time being around 4.5 to 5 minutes. So the chart on this slide is showing a comparison of all of the layouts through each quarter. Looking at the right side of the table, you can see that the first layout resulted in an average percent decrease in pick times of around 12%. And the second layout resulted in a higher average percent decrease in pick times of around 16%. Looking at the information at the bottom here, we are able to say with 95% confidence that the decrease in pick times for the first layout will be between 0.63 minutes and 0.67 minutes. And again, we are 95% confident that the decrease in pick times for the second layout will be between 1.24 minutes and 1.29 minutes per pick list.
And so we'll go into our recommendations and our conclusion on the project. Our first recommendation that we're making to Mike is to adopt the proposed layout 1. This causes no additional cost to him and the company, as it utilizes the current shelf availability, and it did decrease the average order time by 12%. It impacts the company directly by increasing their throughput to 187 orders per day, or an additional 27 orders per day. Our second recommendation is to adopt our proposed layout 2, which is to add that seasonal area right above the shipping area. This does require the use of additional shelves, so it will cause a small cost to the company to implement this. However, it did decrease the average time by just over 16%. It impacts the company directly by increasing their daily throughput by 38 orders, or 198 orders per day. And so now at this point, we'd like to open up the floor for any questions for those in attendance today.
Thank you very much, gentlemen. Also acknowledge that Mike Eldridge, the owner of Safety Glasses, is on with us. So, Mike, thank you very much for being with us this morning, and thank you for allowing our students to work with you on this project. Anyone have any questions for this group?
Thank you, gentlemen, for your time. I don't have any questions, but I appreciate the time and effort you put into the analysis, and we'll definitely be taking some action on things that you've provided.
Thanks, Mike.
Thank you, Mike.
Awesome. Thank you, Mike.
Mike.
And Dr. White thanked all the faculty, but Dr. White, we thank you for introducing us and introducing the teams and all your support throughout the semesters and through the years. So
My pleasure. Thank you very much.
You see the students their first year and their last year, and hopefully a huge difference in between them, right?
Huge difference, and we're so very fortunate to have such terrific students at Western. We get really good kids, and they're really fun to work with, and you can see the culmination of all their work and our work as faculty and how we work together to put them in positions to be terrific engineers. It's very satisfying.
Again, we're proud of all of you guys. We're proud of all our seniors. We're excited to see what you guys go and do. So best of luck to anyone, or not anyone, everyone.
Anybody have any questions before we say au revoir? Well, very good. Thank you, all of you, for joining us. A big round of applause for this group. Thank you for joining the 67th Industrial Engineering presentation of the Engineering Senior Design Projects. We're very glad that you were able to join us. We hope everyone stays safe and has a great day.